Good morning students. Today I am going to explain about the Maxwell equations. So here it is. Hello my dear students. Good morning to everyone. Welcome back to my channel. Before you are going to watch my channel, please like, share and subscribe to my channel. Thank you for watching. So today I am going to explain about the Maxwell equations. So Maxwell equations means here the and electricity and magnetism combinedly together electromagnetism. So the total electromagnetism will be completely explained by these four equations. So that equations are called as Maxwell equations. Here the Maxwell equations will be exist in the two types of the forms. One is Maxwell equations in differential form, another one is Maxwell equations in integral form. So here the Maxwell equations in differential form is del. So del dot E, the divergence of vector, the divergence of electric field. Del dot E means the divergence of electric field. So del dot E is equal to rho by epsilon naught. So rho by epsilon naught, charge density by epsilon naught. Epsilon naught is a constant. So here it is the first equation was proposed by Gauss, the great scientist Gauss. So that's why it is called Gauss law of electricity. So Gauss law of electricity is the equation of del dot E is equal to rho by epsilon naught. Okay. So here Maxwell equations in integral form is very important. So the closed surface of electric field is equal to charge by epsilon naught. So it is known as Gauss law for electricity. And next, the closed surface of magnetic field is equal to completely zero. So it is known as Gauss law for magnetism. Here the Maxwell does not propose the complete four equations. So the first equation is proposed by Gauss. Second equation is also proposed by Gauss. But first equation is known as Gauss law for electricity and second equation is known as Gauss law for magnetism. And third one is proposed by Faraday. So here the third equation is here line integral of electric field is equal to minus dou by dou t of pi b. So it is known as Faraday law for electromagnetic induction. Faraday law for electromagnetic induction. Next, the fourth equation is the line integral of magnetic field of intensity is equal to mu naught into mu naught. Mu naught is here magnetic permeability into current plus epsilon naught into dou pi e by dou t. So it is known as Ampere's law. So here this equation initially proposed by Ampere, further Maxwell add the displacement current. So that's why it is called as Ampere's law. Based on Ampere's law, this complete equation is explained by Maxwell. So this is about the Maxwell's differential equations in differential form. This is the Maxwell equations in differential form. That is Gauss law for electricity, Gauss law for magnetism, Faraday's law for electromagnetic induction. Here B is nothing but magnetic induction. Next, Ampere's law by Maxwell. At the same time, there exist Maxwell equations in integral form. That is same thing, Gauss law for electricity, Gauss law for magnetism, Faraday's law for electromagnetic induction, and fourth one Ampere's law by Maxwell. So let us see Maxwell first equation. So in first equation, so initially there exists the electric flux normal to the surface is equal to 1 by epsilon naught times 1 by epsilon naught times the charge enclosed the surface. 1 by epsilon naught times the charge enclosed with the surface. So here phi suffix e is known as electric flux. Phi suffix e is known as electric flux. So electric flux is equal to 1 by epsilon naught times 1 by epsilon naught times the charge. 1 by epsilon naught times the charge. So that's why here you can write pi by epsilon naught. So but phi e is also known as closed surface of electric field of intensity into ds. That means E dot ds. So surface integral of electric field is also equal to electric flux, and Q is a charge. Charge is equal to charge density. So Q can be written as Q is equal to integral V into rho dot V. So here, so from this we can write that E dot ds is equal to 1 by epsilon naught E dot ds. So pi e is equal to E dot ds. In the place of pi e, we can substitute E dot ds. At the same time, 1 by epsilon naught is same thing. In the place of q, we can substitute rho dot v. In the place of q, we can substitute rho dot v. Now, we get the surface integral of electric field is equal to 1 by epsilon naught into rho dot v. After that, here we can use the Gauss divergence theorem. So according to Gauss divergence theorem, we can write from the Gauss divergence theorem, the surface integral of A dot ds is equal to volume integral of divergence of A vector. So here we can apply for electric field. It can be written as surface integral of E dot ds is equal to volume integral of del operator. Here we can use the del operator. So del dot E dv. But E dot ds is equal to, previously we know that rho by epsilon naught dv. So from we can write integral v del dot E dv is also rho by epsilon naught dv. So the integrals on both sides over the same volume can be cancelled. The integrals on both sides over the same volume can be cancelled with each other. So from this equation we can write del dot E is equal to rho by epsilon naught. So this is the differential form of Gauss law in electrostatistics. This is the differential form of Gauss law in electrostatistics. Okay. And second thing, the Maxwell second equation. So for the Maxwell second equation is Gauss law for magnetism. So according to Gauss law for magnetism, the magnetic flux through surface normal to it is 0. That means the magnetic flux through the surface is equal to completely 0. So this is represents that monopoles does not exist in the magnetism. So that's why here it can be written as the magnetic flux will be completely 0, means flux can be denoted as pi, magnetic flux can be denoted as phi suffix b. So that is completely 0 means it becomes 0. So that magnetic flux can be written as surface integral of B dot ds. So B dot ds is equal to 0. So for B dot ds we can apply the Gauss divergence theorem. So according to Gauss divergence theorem, surface integral of B dot ds becomes volume integral of divergence of vector, that is divergence of B dv. Then if B dot ds is equal to 0 means volume integral of divergence of B is also 0. That's why del dot B dv is also 0. From this we can write del dot B is also 0. So this is the differential form of Gauss law in magnetism. So this is the integral form for Gauss law for magnetism. This is the differential form for Gauss law for magnetism. So B dot ds is equal to 0. Del dot B is also 0. So this is about the completely Maxwell's second equation. This is the Maxwell's second equation. So Maxwell third equation is proposed by Faraday. So according to Faraday law, the induced electromotive force in a closed loop is equal to the negative rate of magnetic flux linked with it. So that means the induced electromotive force, so that can be here denoted as small e. So the negative rate of means dou by dou t of magnetic flux. So magnetic flux can be denoted as pi b. So E is equal to minus dou pi b by dou t. But the induced electromotive force is equal to line integral of electric field. So that is E is equal to integral E dot dl, and pi b is equal to, we know that integral B dot ds, surface integral of B dot ds. Then here we can write if E is equal to small e is equal to minus dou pi by dou t, so in the place of small e we can substitute line integral of E dot dl, so that is equal to minus dou by dou t. In the place of pi b we can substitute that surface integral of B dot ds. So after that it can be written as minus dou by dou surface integral of dou by dou t of B bar into ds. So here we can apply the Stokes theorem. According to Stokes theorem, line integral of electric field is equal to del cross curl E ds, surface integral of curl E ds. So if we apply that, so in the place of E dot dl we can substitute del cross E ds. So surface integral of del cross E ds is equal to surface integral of dou b by dou t ds. So here the integral on both sides over the same surface can be cancelled with each other. If it is cancelled with each other, hence we can write del cross E is equal to minus dou p by dou t. So that is minus dou p by dou t. So it is the differential form of Faraday's law. So for first two equations we can use the Gauss divergence theorem, and next two equations we can use the Stokes theorem. So it is the complete Maxwell third equation. Once if we observe completely, it is very easy. So Maxwell third equation is the induced EMF in closed loop is equal to the negative rate of magnetic flux linked with it. So the induced electromotive force E is equal to minus 2 pi B by dou t. E can be written as E dot dl, pi B can be written as B dot ds. And the last one is Maxwell fourth equation. So the Maxwell fourth equation is based on the Ampere's law. So Ampere's law gives the relation between magnetic field strength around the closed path and current enclosed by the path. So mathematically it can be stated as the line integral of B around the closed path is equal to the mu naught times the current. Mu naught times the current enclosed by the path. Mu naught times the current enclosed by that path. So that can be written as line integral of magnetic field strength. So that is B dot dl is equal to mu naught times the current. But current is equal to, we know that current density is equal to current by area. Then current is equal to current density into area. So that is current can be written as I is equal to surface integral of current density. So that is J dot ds. So in the place of I we can substitute J dot ds. Then B dot dl is equal to line integral of B dot dl is equal to mu naught into surface integral of J dot ds. So here we can use, for line integral we can use the Stokes theorem. So we know that the line integral of the vector is equal to surface integral of the curl of the vector. So that is B dot dl is equal to surface integral of del cross B ds. Then so here B dot dl is equal to this equation, but in the place of B dot dl we can substitute del cross B ds. So del cross B ds is equal to same, it will be repeated here, that is mu naught into J dot ds. So del cross B ds is equal to mu naught J dot ds can be written as J plus JD. So Maxwell here additionally added displacement current density. Okay, now so displacement current density. So extra here we can add displacement current density. That displacement current density is equal to epsilon naught into dou E by dou T. The displacement current density is equal to epsilon naught into dou E by dou T. So that we can written as surface integral of del cross B ds is equal to mu naught into surface integral of J plus epsilon naught into dou E by dou T into ds. So the both sides the surface integral will be cancelled, then it can be written as del cross B is equal to mu naught into J plus epsilon naught dou E by dou T. Here why here displacement current will be added means, so here electric field will be set up current density and magnetic field. So such way that extra current density will be known as displacement current density. So that's why here Maxwell added displacement current density. So these are the Maxwell fourth equations. So these magnetic four equations will be completely explain the total electromagnetic theory. So thank you for watching, my dear students.